Once we've completed the F test, so we have our actual F, we've determined it's statistically significant in the ANOVA, what that doesn't tell us is where those differences are. Now, we can infer that if we have a significant F test, that the group or condition that has the highest value is significantly different than the group that has the lowest value. What we cannot infer and what we do not know is about any other potential differences between those conditions. We're going to still focus on the simplest of ANOVAs, the one-way, three conditions between subjects ANOVA. So we have three conditions. So if we have a significant F test, we definitely know that if group 1 has the highest value and group 3 has the lowest value, those do differ significantly. What we don't know is, does group 2 differ from group 1 and does group 2 differ from group 3? So we need to do additional testing. So the ANOVA tells us that a difference exists somewhere across our conditions, but does not say which groups are different. It's an omnibus test that allows us to know that there is a statistically significant chance at a single test that something is going on in our data set. We now need to find out what that something is. Which groups are different from each other, and that is done through a couple of techniques. The first technique we can do is a post hoc test. It basically acts as a series of paired t-tests. Each group is compared to determine which means differ. It tests all comparisons, and it does raise the type 2 error rate a little bit. So in other words, we are basically taking a little bit of a pass that we've been given permission to go looking for the differences now. Every post hoc test that has been designed and is commonly used has advantages and disadvantages in how it works and how it does this. So just recognize that we're moving into a little bit of a gray zone, but it's a gray zone we're comfortable with because this is an area where, depending on the number of conditions, depending on what's going on in your data set, various post hoc tests may work differently. Some of them may find differences that others don't. Each one has been adjusted to either be more or less rigorous and a little bit more or less focused on that type 2 error rate, making a claim that actually isn't there. Now again, the reason that we're willing to accept a bit more error here is that we already know that there is a statistically significant chance that something's going on. So this is a little bit more of an exploratory analysis. Where are those differences? So that's the statistical technique. The statistical technique is to actually run some form of post hoc test. We can also use a priori approach. Tests only theoretical and important comparisons, maintains or slightly reduces the per comparison alpha. What an a priori approach means is that prior to running our ANOVA, there were certain comparisons that we weren't that interested in. So looking at the criminal, non-criminal, and unknown, we might have already hypothesized that though we have those three groups, and we are going to look at all three groups, we actually don't expect there to be a difference between the non-criminal and the unknown group. It's not a comparison we're interested in. What we're interested in is how both of those groups differ from the criminal group. That would be an example of an a priori approach. I don't need to run a post hoc test on every potential difference. I simply need to ask, is group 1 different than group 2 and 3? So we're going to talk about how we do the a priori approach as well at the end of this slide deck, but first we're going to look at specifically the post hoc test. I do want to at least note that there is one situation in which you would not need to run a post hoc test after getting a significant F. Like I told you, when we get a significant F, the one thing that we know prior to running any of these tests is that the group with the highest value is different than the group with the lowest value. Otherwise, we would have never got a significant omnibus F in the first place. If your a priori hypothesis is specifically focused on those two groups, the group that was highest and the group that was lowest, and the only hypothesis you're interested in testing is whether they were different, well, you know it. You don't need to run any additional tests or even an a priori set of tests. The F tells you that they're different, but that is the only time we would not be running additional post hoc tests once we find a significant F. So let's overview. So the nature of the test effects. The post hoc test generally, and there are more than these three, but these are the three most commonly used. These are the three you'll usually see listed in statistical packages. And again, remember that post hoc tests are a statistical technique. There's Tukey's HSD, and there's Tukey. He at least deserves some fame for him designing this. So this is the HSD test. It's the honestly significant difference test. And the advantage to the Tukey's test is that it basically looks for paired comparisons across the board by setting a new bar. So just like the F test, we had a bar to claim statistical significance. Tukey's test basically asks what is the smallest difference that can occur between means for us to claim that it's honestly significantly different. The disadvantage of Tukey's test, and it is the one that is most commonly used, is that it works best with equal or near equal sample size groups. So this is one of those things that, all things being equal, if you have effectively the similar number of people in each of your conditions, for example, let's say you've got 20, 19, 21, and 20, probably you're fine using a Tukey's HSD. The test is not very effective. In other words, it's more questionable about the results it gives you if there's fairly large differences in your groups. Let's say group 1 had 9, group 2 had 30, and group 3 had 17. That might be an example where we would not want to use Tukey's HSD test. And because it has those limitations, that has resulted in people making additional types of post hoc tests. There's Sheffey's test. And again, I believe that if you actually created something that we see every day, you should at least get a little fame. So here's Sheffey due to a Google search. Anyway, Sheffey's test basically adjusts for this, and it's a more rigorous test. The interesting thing with both Sheffey's and Dunnett's test that we're going to talk about is that both of them may occasionally find results that are counter to the F. In other words, you can have a situation where you have a significant F, and one of these tests, either Tukey's, Sheffey's, or Dunnett's, actually says there are no differences between the groups, even though you already have a significant F test in your pocket. And generally when this occurs, that's one of the other reasons you might try a different test. Also, if you got an insignificant F, in other words, the F test said do not run post hoc tests, and you ran them anyway, sometimes some of these tests may still say there's a difference, even though the F omnibus test said not to look. Now, this is more of a thought exercise. I am telling you as a statistician and as your professor of statistics, if you do not have a significant omnibus F, you do not continue. You do not do post hoc tests. You have no permission to go digging because these tests are kind of digging. They are not precise tests. They're tests that have some positives and negatives depending on your sample size, depending on the type of effects you're looking for. But we allow that little bit of wiggle room of error due to the fact that we've already done an omnibus test. And again, with a priori planned comparisons, we're simply going to run a series of t-tests. The reason, though, that we're doing this is that actually they may still be better at finding the differences because instead of looking at every single difference, which Tukey, Sheffey, and Dennett's tests do, the a priori are only looking for the differences that we indicate. And finally, like I said, there's Dunnett's test, which again has some adjustments. And on the next couple of slides, I'm going to kind of overview the positives and negatives of these three techniques. So basically speaking, it's going from strict to liberal. So Tukey's HSD has a lower probability of type 2 error and a higher probability of type 1 error. So it's kind of general, and honestly, it's the one that if you actually did run Tukey's HSDs on F tests that were insignificant, you'd occasionally find it saying, hey, there's some differences here. In other words, it's kind of set to find differences. And again, it is very susceptible to errors in how it calculates if you have vastly different sample sizes in your conditions that you're comparing. Sheffey's test was designed to actually address this specifically by being a stricter test. It has the lowest probability of type 1 error, but a high probability of type 2 error. So you'd only use Sheffey's test if you really are certain that you've got effect sizes and that you want to be 100% confident that if you claim that effect size is there, it truly is. Sheffey's test is the one that if you will occasionally not find any differences between your conditions, even though you have a significant F test omnibus. So the F test said there's a difference somewhere. Sheffey's test is strict enough or rigorous enough that it's only really looking for big differences. And it may actually claim there's none when you already know there's someone in there. And Dunnett's test is going in the opposite direction. Dunnett basically suggested there are times where, again, if I have an F and it's significant, and I run both a Tukey's HSD, and due to the fact that the sample sizes are different, and I run a Sheffey's test, and due to the fact that it's really looking for big differences, both of them say there's no difference. What do you do? Well, in that case, you'd use Dunnett's test. Dunnett has the highest probability of type 1 error, claiming an effect that's there when it isn't, but it has a lower probability of missing effect. It's a liberal test. It's really set down to dig and find whatever's there. So generally speaking, your order of probability is that most of the time you're going to use a Tukey's HSD. If the Tukey's HSD is giving you some interesting results that don't make a lot of sense, and you have large differences in your sample size, try a Sheffey's test and see if it finds significant differences, and if so, it's probably the better test to report. However, if you are running a statistical test and Tukey's HSD or Sheffey's test, or both of them, are telling you there isn't a difference when you have an omnibus F test, that's when you'd shift down to Dunnett's test. You've been given permission to find the differences. You have an omnibus F. So that's kind of our decision tree, if you will, between these three techniques. All things being equal, use Tukey's HSD. And that's the one we're also going to talk about how to hand calculate. Only use the other ones if you have to. So how do we actually calculate Tukey's HSD? It's a pretty simple test. We take the mean of squared within, divided by small n, and notice again, Tukey's test works best if we have equal sample size. The small n is the same. We take the square root of that and we multiply it by q, and q is a standardized range statistic that we're going to get from a chart. So it determines the smallest difference between means that is honestly significant. We compute the difference score between means of all conditions. So basically, if the difference score between any two means is higher than the HSD, it's significant. So the only thing we really need to run this, that we don't already have either from SPSS or from the actual hand calculations, is Q. And for Q, we simply need to go to the degrees of freedom within. So that's, again, our total n minus the number of groups, and K. Now notice that in this particular case, we're not looking at degrees of freedom between K minus 1. We're actually just looking at K. By the way, the page reference here most likely is from an older book. I don't think it's relevant to your current textbook. So here's the chart. We look at K, number of treatments, and then we look at the degrees of freedom error term. And in this case, we again are looking at that criminal, non-criminal, and unknown group. We have a number of treatments, 3. And again, I really want to stress this isn't degrees of freedom between K minus 1. This is just K. And then finally, degrees of freedom within our error term, which was 12. So 3.77 is our Q for calculating Tukey's HSD. So there's the equation, and we're going to plug the numbers in. The means of squares within, remember, was 5.33. We're going to divide that by 5, the number of people within the group. We're then actually going to calculate that to be a 1.07. We're going to take the square root of that, which is 1.03. We're going to times it by 3.77, and we get 3.88. That is Tukey's HSD. So again, we're taking our error divided by the number of people in any one group, 5, small n, taking the square root of that and multiplying it by Q. So again, what was our means? So our means was 4, 3, and 1. So these are the differences, by the way. Criminal versus non-criminal had a difference of 4 between them. Criminal versus unknown had a difference of 3, and non-criminal versus unknown had a difference of 1. Looking at their means back a few slides in the previous lecture. So again, what we're calculating here is the actual difference between the means. The mean of criminal minus the mean of non-criminal equals 4. The mean of criminal minus unknown mean equals 3. The mean of non-criminal versus unknown, which is 1. So 4 is larger than 3.88. There is a significant difference between criminals and non-criminals. The difference between criminals and unknown is 3. 3 is smaller than 3.8. It's non-significant. And the difference between non and unknown is a 1. Smaller than 3.8, non-significant. So the omnibus F told us that there was a significant difference across our groups, but the post hoc test specifically said the only difference that is significant is the difference between criminals versus non-criminals. So the nature of the effect, criminals had higher antisocial tendencies than non-criminals. There were no other significant differences. Okay. So the a priori test, rather than running a post hoc test, which is adjusted to look at all possible differences, we can look at paired comparisons. We can restrict those paired comparisons to those that we're most interested in. In other words, married versus single. This is especially useful when comparing several conditions. So if we have a data set and we decide to go ahead and run a omnibus test across, say, 7 conditions, but some of those conditions just really aren't that interesting to us. Now, the first thing I would suggest is potentially, if you have no interest in the condition, then don't have it in the model. Don't include that data. You're making your model less likely to find significant differences. So generally speaking, I think the first question you have to have whenever you're considering a priori tests is, should I even have those variables in the initial F model or the ANOVA to begin with? However, if there is a theoretical reason, but you know that you don't want to look at every possible comparison, then again, a priori test may be what you actually want to look for. When we're doing a priori tests, we do have to acknowledge that if we are running multiple t-tests, then we probably need to do an adjustment. So the type 1 error rate, again, of 0.05 is that 5% chance of claiming an effect when it was just due to chance. But that's for when we're running a single test. And there's 2 ways to do an adjustment. The Bonferroni adjustment is a fairly simple method. We're simply going to take our alpha and divide it by the number of tests we're running. So if we're running 3 a priori t-tests on a series of data, instead of an alpha of 0.05 or p-value of 0.05, meaning that we can claim significance, we're going to take that 0.05, divide it by 3, the number of t-tests we're going to run, and that's going to give us an alpha and actually of 0.017. So now we need a p-value of less than 0.017 for us to claim a significant difference. And that's the bottom of the slide, and that's the Bonferroni adjustment. Now, there is a slightly more refined version that gets you a little bit better of a test because honestly, the Bonferroni adjustment tends to overcorrect slightly. And that is the equation here in the middle. The type 1 error with multiple tests, 1 minus parentheses 1 minus alpha raised to c power. So the alpha is, again, probably 0.05 in most cases. C is the number of tests. So again, in this case, if we were actually running 3 tests, we actually would get a new alpha of 0.14. So this method actually is a little more accurate. It's a little more effective. It gets you a little bit more of an actual value. However, either of these are accepted, and there are some additional ways that you can do this. The biggest thing that I want you to recognize is that if you're running multiple t-tests as an a priori post hoc test, you do need to adjust your alpha. So you run the test as normal. It's just the bar for you to accept the statistical significance when identifying group differences is going to be a lower number than the 0.05 you started with. We could also get around this problem by using a priori test to create a contrast, allowing us the collapsing of groups, merging 2 or more groups into one. These broader groups then compare to the group. So again, we have an omnibus F test. We know there's group differences. However, instead of actually doing a t-test, looking at the difference between one particular group and another particular group, we may actually collapse some of the groups into a single variable. So in this case, we'd actually be looking at the difference, for example, between married and single and divorced. We would add the means of single and divorced together and divide by 2. If we had 4 conditions, married, single, divorced, unknown, and we wanted to compare married to all other groups, we could collapse single, divorced, and unknown divided by 3. So this is useful when there is little or no difference between groups. If you make no distinction between single and divorced women, you may put these women into a single group, unmarried. Then compare married to unmarried. So that's another way that we can do an a priori test that actually doesn't require Bonferroni adjustments. So in other words, we started with an actual ANOVA. We had, and I'm going to stick with the 4-group example. We had married women, single women, divorced women, and unknown women. We had 4 conditions. We had values. We get an F test that tells us there is a difference between the groups. But when we actually look at the data, we find that whatever we were measuring, married women have a 7. Single women have a 4, divorced women have a 3.9, and unknown have a 4.1. There's very little difference between those 3 groups. So instead of wasting power looking for differences between them, we could collapse them into a single variable and then compare them to the one group that's different, and then do a single t-test without an adjustment. So the overall message I want you to take away from this is there is no right way to do post hoc testing. However, when we're running an ANOVA, because the ANOVA just tells us there's a difference somewhere, we have to make a choice about how we're actually going to look at those post hoc tests. And generally, we want to make that choice prior to ever looking at the data. If you're doing a priori tests, a priori means before the fact. It means you've already determined what you're going to look at before you get data in hand. And again, broadly speaking, most of this lecture has been about the alternate tools you could use. Most of the time, we're just going to use Tukey's HSD, and that's going to be sufficient for most of the analyses we're probably going to do when we're actually running analyses ourselves.